In a heavy nucleus, a high-energy photon can be converted into two particles, an electron and a positron. A positron has the same mass as the electron and equal but opposite charge. This process is called pair production. Okay, so the first step is to calculate the rest energy of an electron in electron volts. To do that, we're going to use the equation for energy, which is E equals mc squared, and plug in numbers. The mass of an electron is 9.11 times 10 to the negative 31, and c is a constant with speed of light, 3 times 10 to the 8th, and then when we square that and multiply it by the mass, we get 8.2 times 10 to the negative 14th joules of energy. And then to convert that into electron volts, all we have to do is multiply that number by 1 over 1.6 times 10 to the negative 19th joules to make the joules cancel, and we get 5.12 times 10 to the 5th electron volts.
So for part B, we have to determine the minimum energy in electron volts that a photon must have to give rise to pair production. In order to find this, we just multiply the energy by 2. So we take our answer in part A and double that, which gives us our answer here.
All right, so the last part of the problem, part C, is to calculate the wavelength corresponding to this photon energy. So for this, we want to solve for lambda, the wavelength. So we have our original equation, energy equals HF, and you can convert this equation to HC over lambda. H is Planck's constant, C is the speed of light, and lambda is the wavelength which we're solving for. So you rearrange the equation to have lambda equals HC over energy. We plug in the values that we know. H is Planck's constant, which is a constant. C is the speed of light, which is a constant. And energy is our answer from part B. So when we plug those numbers in, we can solve for the wavelength and get 1.22 times 10 to the negative 12 meters.